Welcome back, everyone. In today's lesson, I'm going to discuss some of the information from Chapter 4 of our textbook on early quantum theory. This is going to be essential for us to understand how chemical bonding works later on in this class. Specifically in this lesson, I'm going to talk about ionization energies. We're going to talk about electromagnetic radiation, emission spectra, and black body radiation. So follow along with me in your textbook. We'll work through a couple of the problems in there as well. To begin with, let's discuss what are the basic elements of an atom. We have the protons and the neutrons and the electrons that we've learned so far. We know that protons and neutrons reside in the nucleus, and the electrons are orbiting that nucleus. The protons have a positive charge that attract the electrons, which are negatively charged. The number of protons determines which element that we have. For example, if we have 6 protons, we have carbon. The number of neutrons that we have in that atom determines which isotope of that element we have. So for example, if we have 6 neutrons in carbon, we're going to have carbon-12. If we have 7 neutrons in carbon, we'll have carbon-13, which is a different isotope. And then, depending on how many electrons that we have in that atom, it will determine whether it is a neutral atom or if it's charged. If it's charged, we call this an ion. And if we have too few electrons, if we've removed 1 or 2, we end up with a positively charged atom because we've removed some of the negative charge from that atom. The electrons are negatively charged. That results in a cation that forms. And that's what we're going to start with today. We'll start by looking at what the energy that's required to remove an electron from an atom is. So it's not the same for every atom. Depending on which one that we have, it's going to take a different amount of energy. We'll start by talking about the first electron that's removed and the energy requirement for that. And that's known as the first ionization energy. When we have a higher value, that means it's more difficult for this process to occur. If we look at a graph of the different elements and their ionization energies, which are in the unit of attojoules here, which is 1 times 10 to the negative 18 joules, we'll see an interesting trend where we start with hydrogen, which has a fairly high ionization energy. It's roughly 2.2 attojoules. We go on to helium and see that helium has the highest ionization energy of all the elements. It's 4 attojoules of energy. But then when we get to lithium, the third element in the periodic table, it drops almost to 0.8 attojoules, which is significantly less. And then as we go to the next element and the next element and the next element, this energy requirement starts to increase till it reaches a maximum at neon. We can see that the elements that are in red here, these are all of our noble gases. And the elements that are in blue are our alkali metals, are the first, which is the first group of the periodic table. This suggests some type of a periodicity. And this is part of the reason why the blue elements are all in the same group on the periodic table, and the red elements are all in the same group on the periodic table. Now, as we get to larger and larger atoms, this trend doesn't stay quite the same, right? So helium and neon and argon all have different ionization energies, but we can still see that it kind of goes up and down to here. So when we think of ionization energy, we can think of a general formula that represents this. This would be important for us to know how to do it. So if I have an element, let's say it's got the symbol of X, and I add energy, I can result in the removal of an electron and the production of a positively charged atom. So that's how you would write a general formula for an ionization energy. And then the trend here that we see is as we go right on the periodic table, we increase the requirement to remove an electron. And as we go down on the periodic table, we lower the ionization energy that's required. So far, this is a little bit not helpful. We don't really know about the electronic structure of the atom quite yet. So how are those electrons structured around the nucleus? So in order for us to make sense of this, we'll have to know a little bit more about the electronic structure of the atom. So we'll get to that in a little bit. All right. Now, we can also remove other electrons from the atom. We don't need to just remove the first electron. What we can do is we can look at successive ionization energies. So what's the energy requirement to remove the second, or the third, or the fourth electron from that atom? If we look at this table here, you can see the successive ionization energies for the first 11 elements. We'll notice that hydrogen only has one ionization energy. Why is that? Well, it's because hydrogen only has one electron. For helium, which has 2 electrons, we can remove 2 of them. So that kind of makes sense. That's why this increases as we go down. But what we want to pay attention to is how does that energy requirement change once you've removed 2, 3, or 4 electrons from that atom. If we take a look at carbon, for example, the requirement goes from 1.8 to 3.9 to 7.7 to 10.3. So as we go and remove more and more electrons, the energy requirement increases and increases. This is because as we remove successive electrons from an ion, we must overcome an increasingly greater electrical attraction between the positively charged ion and the electron that's being removed. At some point, though, if I start to remove a 5th electron from carbon, we end up having to pay a much higher price, a much higher energy requirement, 63 attojoules of energy. That's a lot of energy, and it's so prohibitive that carbon very rarely will ever lose 5 of its electrons. In fact, for a lot of these atoms, you'll notice that same trend. At some point, there becomes a point where there's a cost prohibitive effect, where the requirement jumps approximately tenfold. What is this telling us about the structure of the atom? Well, it kind of hints to a shell structure of the atom, where we have the nucleus and we have the electrons that orbit around it. There's inner electrons that are tightly attracted to the nucleus, and then we have electrons that are outside of that, which are less attracted and are more easily removed. So that's our first kind of insight into the atom. So let's look at some of the other text I have written here. So if we go and we want to determine the total energy that's required to remove, say, 4 electrons from a specific atom like carbon, we can simply add the energy of each of these ionization energies to approximate what that total energy cost is. So these are summative energies. That's actually my first question down here. So let's get to that in a minute. Ionization energies are on the order of 10 to the negative 18 joules. These are an attojoule. And we can estimate the total energy needed to ionize an atom by simply looking up these tabulated values and summing them. We should note that these energy requirements increase dramatically as we further ionize the atom. And this suggests that there is these shells around the atom where these electrons are located. An easy way to visualize this is shown here in this graph, where I took the number of electrons removed and plotted it against the natural log of the ionization energy. When we do this, we pretty much get 3 regions. We get region 1, we get region 2, and we get region 3 up here. Each of these regions is a different shell of the sodium atom. Down here is the first electron. This is in the outermost shell of sodium. And then these two electrons that are held very, very tightly, they have the highest energy that's requirement. These are the innermost shell. And then we have 8 electrons that are in the middle shell. And we'll see the number 8 a lot. This will give rise to something we call the octet rule later on when we learn about Lewis structures. To start off, though, we'll talk about Lewis electron dot formulas, which is a convenient way to represent these electrons that are in the outermost shell, which we refer to as the valence electrons. These are the electrons that are the easiest ones to remove from an atom. G.N. Lewis was a chemist that helped us recognize this pattern, and we call these Lewis formulas or Lewis structures in his honor. For a specific atom, when we have a Lewis structure, we call it an electron dot formula. For an element such as hydrogen, which just has one electron, that's going to be in its outermost shell. It's also its innermost shell. That will just be represented as its elemental symbol with a dot. So hydrogen dot. If we go and we want to represent helium, helium is going to have 2 electrons. And we can put the dots together or on either side of the symbol. All right, so let's go on and write a couple more of these out. So for lithium we saw has 1 electron that's easily removed, but then we go on to remove the second one. Okay, so these must be the inner electrons. So we're not going to represent those in this Lewis electron dot formula. We're just going to write 1 electron like this. Another thing that we could do is we could represent this using the noble gas configuration. So lithium has 2 electrons that are inner, which are similar to the electrons of helium, and then it has 1 extra electron. So this notation here is a very interesting one, which will be really helpful. All right, and then we have our next atom, which is beryllium. Beryllium has 2 valence electrons. We could also write it as helium with 2 electrons. The next element is boron. Now, boron has 3 valence electrons. So this is the first element with 3 valence electrons, and we can put one on each side of boron. The inner shell notation would be helium with 3 dots. And then carbon is going to have 4 dots around it. We can continue to do this with the rest of the second row. Let's go ahead and just do that. So we'll have nitrogen, oxygen, fluorine, and neon. And when we do this, we do these next ones, we'll have to start pairing up these electrons. So, and why we'll pair them up will be discussed very soon. Okay. So we'll put dots around it, and then we'll pair them up individually. Okay. And then we get to neon, which has 8 outer electrons, 8 valence electrons. And then we get to the third row of the periodic table, because at this point we'll see that we have filled up all of the outermost electrons. And then at some point we need to now add another shell. So we're going to find that sodium is just going to start repeating where lithium left off. But the inner core notation for sodium now is going to be the same as neon now with 1 dot. Okay. You can even represent If you want to do neon itself, you could just write it like this. This is kind of a corny notation, but it's done a lot as well. So, all right, let's practice this a little bit. We have a couple problems. I just grabbed these from the textbook. They're in the back of the book. The first one is to calculate the energy requirement to form a single carbon 4+ ion from a neutral carbon atom in the gas phase. Before we do this, let's write out what the ionization energy equations would be. A neutral carbon atom was just carbon, and then we need to add in a certain amount of energy, so we can find that in the table here. So 1.81, and these are attojoules, will give us carbon singly ionized and the ejection of 1 electron. From there, we can go and ionize that ion further, and we need to now add 3.90 attojoules. And then we go on and ionize it one more time, 7.67. And the last one is 10.3. Okay, and the total energy that's required is 23.68 attojoules, or we could write 23.68 times 10 to the negative 18 joules, which, if we want to put it in proper scientific notation, would be 2.368 times 10 to the negative 17 joules. We can also do this in terms of kilojoules per mole. A lot of textbooks and a lot of databases, instead of using attojoules, will do it this way. So let's do a unit conversion. Let's take this number and convert it into kilojoules per mole. All right, so what we need to do here is we need that conversion factor between atoms and moles, and that is Avogadro's number. So there are 6.022 times 10 to the 23rd atoms per mole. And one way to kind of think about these units is this is the energy per atom of carbon. So if you're struggling with the scientific notation, which I'm always trying to think about the best way to explain this. So let's do it like this. Then we can see that the units do cancel properly. So atoms of carbon cancels out. And then we're going to get joules per mole. But we want to get kilojoules per mole. So what we might want to do at this point is convert joules to moles, joules to kilojoules. There is, in 1 kilojoule, 10 to the 3rd joules. And then all my units will cancel out. So I like to use dimensional analysis whenever possible. It's not going to be used for every problem in this lesson. Right, so for this one, we get that the answer is 14,260 kilojoules per mole. We want to put that in scientific notation. What does that come out to be? 1.426 times 10 to the fourth. All right. I have a couple of problems here about writing Lewis electron dot formulas. Now, these are ones I didn't talk about, aluminum and chlorine. But what we can do is we can just look at the periodicity of these elements. Aluminum is in the same place that boron would be on the periodic table, just one row below it. So a boron and aluminum are in the same group. And then where's chlorine at? Well, chlorine is in the same group as fluorine. So based off of this information and this chart, we can assume that aluminum and chlorine are going to have the same number of valence electrons as boron and fluorine, respectively. So for aluminum, we can look at what we wrote down for boron. We said that there was 3 dots, 1, 2, and 3. If we wanted to write the inner core representation, we would want to start with neon instead of helium. So it's got the neon notation, 1, 2, 3. And then for chlorine, it's got the same number of valence electrons or outermost electrons that fluorine would have. It has 7. And the inner core notation for that would be neon with 7 dots around it. We can also extend this to write out Lewis electron dot formulas for ions. Aluminum 3+ is going to have 3 less electrons than neutral aluminum. So if we remove these 3 dots, we'll end up getting just aluminum. Or we could write neon. So when we remove 3 electrons from aluminum, it now has the same core notation as neon does. And this is the reason why if we go to try to remove another electron from an element such, like, let's talk about sodium, for example. If I go and I try to remove the next electron here, this one is going to have the same number. This is going to be like trying to remove an electron from neon. And when we try to remove an middle or inner core shell electron, it's very cost prohibitive. So we have those easy ones to remove on the outside. We've removed all 3 of those for aluminum. Now we have to start removing ones from the inner core, and that's less favorable. And then for chlorine, here we're having a negative charge, so we're going to add 1 more electron. That's going to fill up our octet, fills up all of our valence electron spots, and it gives us the core notation for the next noble gas. So the next noble gas is argon. All right, so having a periodic table here, it's pretty helpful. I have a lot of these in my head, right? So I'm not really looking at the periodic table, but you might need to for some of these. All right, so to start, to continue on with the lecture, we want to understand how matter and light interact together. This is going to be crucial because what we'll be doing with a lot of these next experiments is just taking a light source and shining it on matter and seeing what happens. And for us to understand what results, we really need to understand what light is. A lot of these images are from the textbook. You can go and read a little bit more about it there. But light is made up of waves of electromagnetic radiation. If you've taken physics, this will be a review. If not, this will be a new concept for you. Electromagnetic radiation are waves of oscillating electric and magnetic fields. So you can see here we have an electric field that oscillates like a wave, and then we have a magnetic field that oscillates here like a wave. They oscillate perpendicular to each other and perpendicular to the direction of the travel of that light source. So the light begins here and it's going in that direction. So that's a light ray. The entire spectrum of electromagnetic radiation is called the electromagnetic spectrum. And we can organize all the different types of light or all the different types of electromagnetic radiation by the property of its wavelength or by its frequency. And I was talked about how these are inversely related to each other, so we can just talk about one or the other. But we'll see that there are 7 major regions of the EM spectrum. At the highest wavelength side, so the longest waves of light, we have radio frequency. So radio waves are very, very long waves. And then on the other end are gamma rays. These are very, very short waves. Or conversely, they're very high frequency waves. And then we're more familiar with regions like the microwave region. So when we heat our food in a microwave, we're using radiation in this region. Infrared radiation is radiation that we emit as a hot object. We're always radiating out infrared. Visible light is this small region of the electromagnetic radiation that we can see with our eyes. So visible light only makes up a small portion of light. And then ultraviolet radiation is this little bit higher frequency light than visible that we can't observe, but we know that obviously we can feel it when we go out in the sun. We can get sunburnt. And then X-rays, that's a really interesting way that we can probe and look at the inside of our body, right? So we can use X-ray sources. But what are wavelengths and what are frequencies? So let's look at the definitions here. Let's start with frequency. So a low frequency wave is going to have less cycles per second. So say, for example, these are all the waves. This is the wave in 1 second here. So here I have 1, 2, 3, 4 cycles per 1 second. But this high frequency wave has many, many more cycles in that given time frame. Whereas the wavelength is the distance between the crests or between the troughs on that wave. This is a longitudinal wave. We can also have waves that exists in this direction, but we'll discuss longitudinal waves here. And then we can see that for high frequency waves, they have short wavelengths, and low frequency waves, they have long wavelengths. So they are inversely proportional to each other. Wavelengths are typically given by the Greek letter lambda, and they are given in units of meters. Frequency by the Greek letter nu, which looks like a V, but it's slightly different, and it has units of hertz or inverse seconds. A hertz is 1 cycle per second. We never write cycles per second, though. The cycle is implied. So we'll see inverse seconds and meters. And then high energy, we'll talk about in a little bit, is associated with high frequency and short wavelengths. The speed of a wave is its wavelength times its frequency. And for electromagnetic radiation, all of these waves travel at the same speed. They all travel at the speed of light in a vacuum, which is 2.998 times 10 to the 8th meters per second, which is sometimes referred to as the speed limit of the universe. So nothing can travel faster than the speed of light. The visible spectrum, again, is just a small portion of the EM spectrum. I'll talk about that in a little bit. Okay, so this equation here helps us relate the speed of light with a wavelength and a frequency. So given any wavelength, and we know that if we have an electromagnetic wave, we can find its frequency and vice versa. let's practice that with a couple of these. And one thing to note is that we always need to convert our prefixes back to the base units whenever we use an equation. So if I want to find the frequency of a violet light, that is 400 nanometers, we need to first convert it into meters, and then we can apply that equation. So let's start by writing the equation that we need. So if we have speed of light equals lambda times nu, we want to find nu. I can divide both sides by lambda to get that the frequency is equal to the speed of light divided by the wavelength. Speed of light is 2.998 times 10 to the 8th meters per second. And I'm going to use this notation in like s to the negative 1 here. And the wavelength is 400 nanometers. But I need to convert that first to meters. So 400 nanometers, a nanometer is 1 billionth of a meter. So 1 nanometer is 10 to the negative 9 meters. And you can do this portion separately, or you can do it afterwards. I always do it like this. So my calculator, I'll use some parentheses, because this will be my denominator. So I'll do 400 nanometers times 10 to the negative 9. So the easiest way to do that would be times e to the negative 9. And that results in 7.5 times 10 to the 14th. And what are my units here? So frequencies are given in terms of inverse seconds. And we can see that when we cancel our units, meters cancel, nanometers cancel, and we're left with inverse seconds, which if we'd like, we could write 7.5 times 10 to the 14th hertz. When you do these problems, your frequency values will always be a large number like this. There's a lot of cycles of light traveling per second in visible light. This seems like a really big number, but that is in fact correct. And then a radio station broadcasting at a certain megahertz. We can actually find the wavelength from this frequency. So when we listen to AM or FM radio stations, they are going to list on the radio how many megahertz it's being broadcast at. So this is a frequency. The capital M is mega, which stands for 1 million hertz. So 89.6 million hertz. Let's start by rewriting this equation for lambda. So what I want to do is solve for nu and I'll divide both sides by lambda. Oh, I'm sorry. I want to solve for lambda. I want to find the wavelength. So wavelength is lambda. So I'll divide both sides by nu. Lambda equals c over nu. And this is similar to the last problem. We're going to need to convert the megahertz to hertz. So I'll write it like this, and times 10 to the 6th. Oh, I guess let me show you how I got that. So megahertz. So there is in 1 megahertz, there is 10 to the 6th hertz. And we can do this conversion factor. Forget it. Okay, so let's do this first. So if I have a graphing calculator, a lot of times if I do second enter, I can pull up that equation so I can save a little bit of time. So let's do 89.6 times 10 to the 6th. That would be times e to the 6th. We find that the wavelength is 3.35 e to the 0, which is just the first power. So I can show you that it's just 3.35 meters. So when we're canceling out units here, inverse seconds is the same as a hertz, and then a megahertz and a megahertz cancel out. Okay, so those are very long waves that are traveling. That's part of the reason we need a very long antenna to detect the radio frequency waves that are coming through the air. All right, so now that we know a little bit about how light behaves as a wave, let's look at the individual waves that are contained in white light compared to when we have an excited atom and we observe what type of light is being emitted by an atom. Okay, so if I have a source of white light, which means it contains all the wavelengths of visible light that we can see, and I use a prism to separate out all the different wavelengths of that electromagnetic radiation, we'll notice a continuous spectrum. Here I have violet on this end, and I have red on this end. So we have Roy G. Biv. That's how I always remember the colors of the rainbow. Red, orange, yellow, green, blue, indigo, and violet. And we see a continuous visible spectrum, and there are no gaps here. So there's no black lines anywhere in this spectrum. However, when we take an excited elemental sample, say for example hydrogen gas, and we pass it through a prism, so I have a discharge tube containing hydrogen, and we have some aligning slits so that we can get all the get all the wavelengths in a single line, pass it through a prism, we can then detect that instead of getting a continuous spectrum, we get 5 discrete lines in the visible light spectrum. We have on one line of red, one line of green, blue, violet, or I guess indigo and violet. This last one here, I've never noticed this 397 because my eyes aren't very good, but I'll notice these 4 lines. And this emission spectrum of hydrogen is really interesting. It's a characteristic fingerprint that's not continuous, but rather discrete. And Johannes Balmer was studying this. He was a Swedish scientist, and he wanted to try to understand how to make sense of these lines. So him and Johannes Rydberg derived an empirical equation to help represent these discrete lines of hydrogen. If you take the reciprocal of the wavelength, so 1 over the wavelength, and plot it against 1 over n squared, where n is any integer from 3 and so on, you'll end up getting a straight line that passes through this. So I was playing around with this earlier, so you can, I was just using Excel. It's shown also in your textbook, but you end up getting these. This is the x-axis here. I didn't label it. This is 1 over n squared, and then this is 1 over the wavelength. And we get a line that fits this data really, really nicely. We have 5 data points, and we get a trend line that gives us this number, 1.97 e to the 7th times x. That's our slope. That number there is the Rydberg constant. This constant it's just an empirical a number that fits the data. And it doesn't really tell us anything more than that this really is a great way of predicting what these lines should be. We take the Rydberg constant, we multiply it by 1 over 4 minus 1 divided by n squared, where where n can be 3, 4, or 5. And we find that it fits the data perfectly. And we can do this not just for hydrogen, but we can do it for all of the different elements. And the study of these types of lines is known as atomic spectroscopy. And each atom gives a characteristic fingerprint. We can see here mercury's lines, helium, lithium, thallium, just has one line there. And everyone is very uniquely different. Sodium gives us this beautiful yellow line here. So a lot of the street lights, they've changed over since I was a youngie. But there's this yellow line of sodium that you can see. So a lot of street lamps that are older will have a very yellow glow to them because they're mostly sodium lamps. But yeah, so you have an interesting set of lines for each of these elements. And then if we can extend this region of the electromagnetic spectrum out to infrared and ultraviolet, so I need a detector that can detect in those regions, we'll also get distinct lines. We call the visible series the Balmer series. And then there's the ultraviolet series and the infrared series. And each of these tells us a little bit more about the atomic structure of these elements and about how light interacts with matter. But we still don't really understand at this point why these lines are coming about. Why don't we get a continuous spectrum? Well, that was figured out, I guess, by Max Planck in 1900 and Albert Einstein in 1905. So let's talk a little bit about the first of these discoveries, which was the study of black body radiation. And then in the next lesson, I'll talk about the photoelectric effect. So let's start off by talking about that all solid objects emit thermal radiation. And the best of these emitters of thermal radiation are termed black bodies, because not only are they going to emit radiation perfectly, but they're also going to absorb all incident light on them and appear black because they're absorbing all those colors. When an object is very hot, it may begin to appear red hot. So you can think about when you're heating your stove and the stove becomes red hot. And it becomes red first because that's the longest wavelength of visible light. As you begin to heat the object further, it may become white. It becomes white hot as it begins to emit all regions of the visible light spectrum. Upon further heating, it may even become blue as the intensity of the blue wavelengths outcompete the red wavelengths. And the study of black bodies in the late 1800s showed that the intensity of the light reaches a maximum as the wavelength decreases into the ultraviolet range, and then it sharply decreases to zero. So these black bodies, the only thing that really determines them is, how do I want to put this? We can characterize these black bodies by the temperature that they emit. And we have 4 lines here, a 3,000 Kelvin hot body, 4,000, 5,000, and 6,000. And as that object gets hotter and hotter, the maximum wavelength decreases. So we'll see that it goes from 1,000 roughly here to 750 to 600, and then roughly to 500. And then if we were to get that object even hotter, it would shift more and more to the left. But at some point, it drops off quickly to zero. And this is the dilemma because according to classical mechanics, what was predicted was instead of a drop off to zero, it was predicted to just kind of go off indefinitely. And this was known as the ultraviolet catastrophe because as that black body emits radiation in the ultraviolet region, it was predicted to give essentially increasingly higher levels of energy to a point where it would be radiating off infinite energy. So this was not physically possible. We can't be radiating infinite energy. That makes no sense. So Max Planck resolved this paradox by proposing that instead, electromagnetic radiation can't be emitted or absorbed continuously. It can only be emitted or absorbed in discrete quantities, which he called quanta. The singular of that is a quantum. And this energy is proportional to the frequency of the radiation that's either emitted or absorbed. And Einstein later called these photons. So I'm going to use that term as well, photons. And at low frequencies, it costs little energy to emit quanta. So it's really easy to emit quanta at low energies. But as the frequency increases, or conversely, as the wavelength decreases, it becomes more prohibitive to do so because the energy cost of a quanta becomes more and more and more. We can represent this by the equation of the energy of the photon, or the energy of the quantum is equal to this proportionality constant known as Planck's constant times the frequency of that radiation. And Planck's constant was derived empirically based off of data. It came out to be 6.626 times 10 to the negative 34 joule seconds. This is a really, really small value, showing us that light packets come in very, very small quantities of energy. And this is the reason why classical mechanics couldn't predict this, because it didn't have any assumption that light was carried in these individual packets. It just assumed it was all continuous energy. Now, and that you can't really see that until you get to the atomic level. All right. We can also write the equation as the energy of the photon is equal to Planck's constant times the speed of light divided by the wavelength of the light. So here we're just making use of that equation from up above. All right. I'd like to try a couple problems with you. These are problems I found in the textbook, so you can find some similar ones and practice them on your own. The first one is to try to calculate what the energy of an X-ray that has a specific wavelength is, and then is that sufficient energy to ionize an argon atom, which has an energy requirement of 2.52 attojoules. And one thing we want to keep in mind for the second part of this question is that if the energy of that X-ray is less than that amount, it's not going to be sufficient enough to ionize it, because it has to meet the energy packet requirement. It has to be at least 2.52 attojoules. So if that number is less than that, this won't be enough. This quanta won't be enough energy. So what we'll start off by doing is making use of this equation the second one I have written here, because I have a wavelength. I have two constants. I have Planck's constant, I have the speed of light, and then I want to find the energy. So we'll just essentially plug that in. So the energy of the photon, or the energy of the quantum of X-ray, is equal to Planck's constant times the speed of light divided by the wavelength. Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And the speed of light is 2.998 times 10 to the 8th meters per second. And the wavelength is 80 nanometers, which we need to convert. 1 nanometer is 10 to the negative 9 meters. So the energy of this X-ray is 2.48 times 10 to the negative 18 joules. And we need to convert this to attojoules. So 1 attojoule is 10 to the negative 18 joules. And 10 to the negative 18 over 10 to the negative 18 will just give me 2.48 attojoules. And this energy is less than the requirement of 2.52 attojoules. So this X-ray source isn't quite enough energy to ionize argon. It's close, but not quite enough. The second question is one I really like because it results in a very fascinating number. So let's just solve this problem, and then we'll try to rationalize the meaning of this. So what's the minimum number of photons or quanta of green light that can be detected by the human eye if 2.35 times 10 to the negative 18 joules of green light is the least amount of eye that the eye can detect? First off, what is the energy of a quantum of green light? Well, we have 510 nanometer light, and I want to find what the energy is. So the energy is equal to Planck's constant times the speed of light divided by the wavelength. So essentially everything that we did just above. So I'll just modify this so it's 510. All right, so the energy of a photon or quantum of green light is 3.895. We'll round it to 2 sig figs, 3.9. Let's see. Let's do 3 sig figs. 3.895. So 3.90 times 10 to the negative 19 joules. And this number is less than the energy requirement that's needed to see the green light. That means we need at least we need more than one photon of the green light. So we can't detect a single photon, but we need a couple of them, right? So we'll have the energy requirement divided by the number of the photons will give us the energy of a single photon will give us the number of photons. Okay, so we need 2.35 times 10 to the negative 18 joules. This is the joule per photon. And what do we get? We find that the number of photons is roughly around 6. 6.03 photons. Well, we can't have a fraction of a photon. So we might want to round this up to the next integer. So we need 7 photons of green light. And that's fascinating because our eyes are very sensitive detectors of light. They've evolved over a million of years to detect light. We have cone receptors in our eyes that can take the light and transmit it into a chemical signal. If you go on to study biochemistry, you'll learn more about the different receptors in the eye that are responsible for this. And it's just fascinating to me that that's the result. And then I have one last question here, and it ties into some of the stuff that we learned earlier. The question is to calculate the frequency and wavelength of photons that are capable of just ionizing 1.0 times 10 to the 16th sodium atoms in the gas phase. And then if we assume that the ionization efficiency is 16%, how many of those photons are needed to ionize the sample? So again, we have 2 questions here. And I grabbed some information from earlier in the lesson. We have the successive ionization energies for sodium. 0.83 attojoules is the energy for removing the first electron of sodium. Now, it doesn't say we need to remove all of the electrons. It says to just ionize it. So that means just removing 1 electron. So the energy requirement to remove this first electron has to have a energy that's at least 0.83 attojoules. It could be more, but the requirement is this number. So let's start with that. So the energy required, how do I spell required? Okay, which is 0.83 times 10 to the negative 18 joules. What we then can do from here is convert this into frequency and wavelength using the Planck-Einstein equation above. So that's E equals H times nu, or E equals H times C divided by lambda. And then we can remember we also have this equation, C equals lambda times nu. What I usually like to do is I'll calculate this one first because it's the fewest number of variables. So to find the frequency, we can take the energy, divide it by Planck's constant. All right, this frequency is 1.25 times 10 to the 15th inverse seconds. And then the wavelength of this light can be determined just using this equation, or we can plug it into this one. Either way works. I'll do it this way. So we'll take wavelength is equal to the speed of light divided by the frequency. And we find that the wavelength here is 2.39 times 10 to the negative 7 meters. If I want to convert that to nanometers, we can multiply it by 10 to the 9th to get that the wavelength of this light is 239 nanometers. What did I do here? All right, so which portion of the electromagnetic spectrum is this light in? 239 nanometers is of a higher frequency than violet light, so this is in the ultraviolet region. Or UV portion of the EM spectrum. Hi, Princess. All right, the last portion of this question is asking how many of these photons is needed to ionize the sample. Well, we want to find, we need 1 times 10 to the 16th ions. And if we have a 16% ionization efficiency, that's the same way of saying for every 100 photons, only 16 of them will give us ions. And it's essentially dividing by 16%. If we did it the other way, it wouldn't make sense. The answer would be off. It would mean that we'd require less photons. So here we find that we need at least 6.25 times 10 to the 16 photons of this UV light. Okay. Well, we'll continue our lesson by understanding the photoelectric effect, the de Broglie wavelength equation, which will help us understand how light is both a wave and a particle, and how that pertains not just to light, but other particles as well. We'll talk about the Heisenberg uncertainty principle, which is really fascinating, and that would allow us to then go on and learn more about electron configurations. And I hope this lesson was helpful for you. And let me know if you have any questions. Have a great one.